Let's use this video clip, take a look at how we can determine what the appropriate units are for a rate constant K that appears in a rate law expression. In a rate law, the units of K can vary depending on whether the order of the reaction is first order or a second order or something such as a 3/2 order even. But the strategy that we can use to figure K remains the same regardless of what the order of the reaction may be. A key thing in figuring out what the K units should be is understanding that rate is always measured in terms of moles per liter per time. That the rate of a reaction is a change in concentration, which is moles per liter, and how much time goes by for that change to take place. So it's moles per liter per time is always a unit of measure for our rate of reaction. Now moles per liter per time could also look like this, where we might see moles over liter times time, which is the same thing as moles per liter per time. Or this might appear as something like a capital M for moles per liter, and that over time, which is the same thing as a capital M times time raised to the -1 power, as ways we might see the rate of a reaction expressed. But no matter how it's expressed, it's always in terms of change in concentration per time, which is moles per liter per time is ultimately what the rate of reaction is expressed in. Let's start by looking at this reaction where we have a second order reaction and we want to figure out what should be the appropriate units for our rate constant K. Our rate is going to be in terms of moles per liter per second. So this is how our rate would look. We're going to use seconds as our unit of time in this first example. Now concentration for A is measured in terms of moles per liter. And because we're second order, this means it's going to be whatever the moles per liter is squared. So if we have our unit of measure, which is concentration of A inside the bracket, which is moles per liter, because we have second order, that's the same as moles per liter times moles per liter, which gives us our unit right now of moles squared per liter squared. Given that we know right now that we have moles squared per liter squared, the unit of K needs to be whatever it needs to be, so that when we multiply K times moles squared per liter squared, we end up with moles per liter per second. Now since we have liters squared in our denominator here on the right side, but only liters here on the left, we need to get one of our liters to cancel. So that means in the numerator of our K, the units for K, we have to have a liter. We also see that we have moles squared here, but on the side with rate we only have moles. So we have to reduce this from moles squared to just moles. So our denominator is going to have moles. We also notice here we have seconds. So our constant here would be the liter per mole second, in that if we multiply whatever our K is with this unit, liter per mole second, times moles squared per liter squared, the moles here will cancel. One of the moles here cancels, so our square reduces just mole. This liter will cancel, reducing this to just a liter, and the seconds that we have here does not cancel. So we end up with, on the right side now, is the mole per liter second, which is the same unit that we have over here for our rate of reaction. So this means this unit that we have Let's look at a different reaction to determine our unit of measure for the rate constant K. Now this reaction is fourth order overall. Now if we take A, which is concentration measured in moles per liter, times our B, which is the third power, where B is also moles per liter, we end up with the term of moles to the fourth liters to the fourth. The unit of measure that we have for our K now needs to be whatever it needs to be, so that when we multiply our K times moles to the fourth liters to the fourth, we're left with, in this case, moles per liter minute, We're using minutes for our unit of time in this example. Now as we look at this, we can see we need to reduce our moles that we have in the numerator from moles to the fourth to just moles. So that means our denominator in a constant will have moles raised to the third power. Because we have liters to the fourth here and we want to end up with only liters, our numerator will have something liter to the third. And because we have minutes here, we need to have a minutes in our denominator, so this is moles cubed times minute. If we now multiply through our K constant, our liters cubed will cancel, reducing liters fourth just to liters. Our moles cubed will cancel, reducing our moles to just moles. Nothing cancels out with our minute. When we look at everything that doesn't cancel out, it leaves us with moles per liter minute, which is the same thing as what we have for our unit of measure for the rate. So what we have here would be our appropriate unit. The liter cubed per mole cubed minute would be our appropriate unit of measure for our rate constant in this particular rate law. Do another example. In this case, we have a reaction that is a overall order to the 2.5. We have x to the 3/2 and y to the 1. 3/2 with respect to x and first power with respect to y. Our rate again is in terms of moles per liter per time. In this case, we have it moles per liter per hour. We're going to use hours as our unit of time in this example. When we multiply through our concentrations of x and y raised to their respective orders, we end up with where our unit right now is the moles to the 5/2 over liters to the 5/2. The value for our K unit now needs to be whatever it needs to be, so that when we multiply everything together here, we're left with moles per liter per hour as our unit of measure. Since we have moles in our numerator over here, we'll need moles in our denominator in our rate constant. Since this is to the 5/2, we want to reduce that essentially to just the 2/2 or the first power. So our moles here needs to be to the 3/2 power. Likewise, since we have in our denominator here, we have liters to the 5/2, we need liters in our numerator, and here we have our liters to the 3/2. We have hours in the denominator here, so we have to add in hours in our denominator on our rate constant. So in this case, the unit of measure for our rate constant is the liter 3/2 mole 3/2 per hour. In that, if we cancel out our moles to the 3/2, that'll reduce from 5/2 to 2/2, which is the same thing as moles to the 1. Our liters to the 3/2 cancel, reduces this to the 2/2, which is the same as to the 1. Our hours do not cancel. This leaves us with the mole per liter hour, which is the same unit as we have for our rate of reaction. So that verifies that our unit we have for our rate constant K is correct.